Welcome back to The Explainer. I am absolutely thrilled you're joining me today because we are finally popping the hood on the absolute workhorse of quantum computing. We're demystifying the true engine of it all, multi-qubit gates. So let's just jump right in. At the very heart of quantum information processing lies this massive, almost impossible physical challenge. How exactly do you make two individual atoms, these incredibly fragile qubits, actually talk to each other without completely destroying their quantum secrets? That is the foundational puzzle we are unpacking today. To get there, here's our roadmap. We'll start with beyond single qubits, explore the multi-qubit gate zoo, examine entanglement and computational power, look at how we're building quantum hardware, and wrap up with code-breaking and real-world impact. Okay, Section 1, Beyond Single Qubits. Look, if we only had single qubit gates to work with, honestly, a classical computer could easily dwarf a quantum computer's power. To generate that real, world-changing computational muscle, we absolutely need multi-qubit gates. By definition, these are reversible, unitary transformations acting on a set of qubits, where no information is lost. The absolute crucial word here is reversible. In quantum mechanics, it's a strict rule. Whatever goes into the gate must be entirely deducible from what comes out. You literally cannot lose a single drop of information. Contrast that for a second with classical logic gates. Your standard AND gate is essentially an information shredder. Think about it. If an AND gate spits out a 0, you have absolutely no idea if the inputs were 0 and 0 or 1 and 0. That historical data is just gone. The past is erased. Quantum gates, because they act as reversible unitary matrices, are a totally different ballgame. They have the absolute necessity of preserving that delicate quantum information from start to finish. Moving right along to Section 2, the multi-qubit gate zoo. Let's meet the programmable building blocks of our quantum circuits. There are three major multi-qubit gates you definitely need to know. First up is the controlled NOT, or CNOT gate. It looks at a control bit, and if that control is a 1, it flips the target bit. If it's 0, nothing happens. Pretty straightforward. Second, we have the controlled Z gate. This works similarly, but instead of a flip, it applies a poly Z phase operation to the target if the control is 1. And third is the swap gate, which, exactly as it sounds, just exchanges the states of two qubits entirely. The massive takeaway here is that a control bit dictates the action on a target bit, but the control bit itself remains completely untouched. Now let's level this up with the Toffoli gate, also known as the double control NOT. Think about the logic structure here. You have two control inputs and one target. The target only flips, say from a 0 to a 1, if both control 1 and control 2 are exactly 1. And again, the control bits remain completely unchanged on the other side. This brilliant double control mechanism safely and reversibly replicates classical and operations, but without shredding any of that precious information we talked about. Which brings us to Section 3. Entanglement and computational power. Let's see what happens when we chain these together. So, why do we need these multi-qubit gates so badly? It all comes down to the Kronecker tensor product. Conceptually, this means adding just one single qubit literally doubles your computational vector space. 2 qubits create a 4-dimensional state. 3 qubits make 8 dimensions. By the time you string together just 50 qubits, the sheer exponential dimension of that state vector rivals the memory limits of the most powerful modern supercomputers on Earth. It's just a mind-bending scale. But the real magic isn't just the sheer size of the space. It's what actually happens inside it. As Azure Quantum puts it, the information is stored non-locally in the correlations between the two states. When a multi-qubit gate like the CNOT acts on qubits, it creates an entangled state. You can no longer describe those qubits individually. The information isn't sitting on qubit A or qubit B anymore. It lives in the unique, non-local correlation between them. That exponential explosion of shared processing space, that is the true superpower of a multi-qubit gate. If you break down the math of a general 3-qubit unimodular orthogonal gate, like the models from WrittenPress, it can sound pretty intimidating. But what's really happening is quite elegant. These incredibly complex 3-qubit mathematical operations are synthesized, or basically broken down, into sequences of simpler multi-qubit gates. Specifically, we're talking about combinations of CNOTs and elementary single-qubit rotations, like RY and RZ. When you divide these operations down into smaller subcircuits, theoretical physics has to step in and set some strict boundaries. For instance, researchers found that a general 3-qubit unimodular orthogonal gate can be synthesized using a strict maximum of 16 CNOT gates in the worst-case scenario. Why do these hard mathematical limits actually matter?
because keeping these circuits as tiny as possible is absolutely essential. Every single extra gate is a liability, so fewer gates mean fewer physical errors when we actually go to build them.
And that leads us to Section 4, Building Quantum Hardware, the real-world physical struggle. Because let's face it is one thing to draw a CNOT gate on a whiteboard. It is an immense engineering feat to actually build one. The timeline of hardware breakthroughs is wild. Back in 1999, the Mølmer Sørensen gate was proposed to entangle trapped ions using lasers. Jump to 2019, and Google's Sycamore processor used entirely different hardware, superconducting circuits called transmons. In 2025, Parity QC developed a new architecture using error correction codes. And just recently, in 2026, researchers demonstrated global parametric gates, achieving multi-qubit entanglement in a single step. These are entirely different physical architectures, but they're all just different ways to implement the exact same multi-qubit logic. Let's zoom in on a couple of these, starting with Google's Sycamore. They used a 2D array of 54 qubits utilizing a flip chip design with superconducting indium bumps. But the real engineering hurdle, that was the 88 tunable couplers placed between the qubits. See, when you pack qubits close together on a chip, they accidentally talk to each other through parasitic crosstalk. It's like trying to have a private conversation in a crowded, noisy room. These tunable couplers allowed engineers to just switch off those stray interactions, keeping the qubits isolated, and then pulse the coupling on for just 10 to 20 nanoseconds to perform a fast, beautifully clean multi-qubit gate. Now, contrast that superconducting approach with trapped ions. The Mølmer Sørensen gate uses red and blue sideband lasers to vibrate the ions and force an interaction. Recent breakthroughs there have achieved over 99.99% gate fidelity, which is incredible, without even needing perfect ground state cooling. And looking at that 2026 breakthrough we mentioned, researchers are now using microwave parametric drives on fixed-frequency qubits to generate massive 2, 3, and 4 qubit entanglement globally, all in a single step. That completely bypasses the need for a long, error-prone sequence of smaller CNOT gates. And we absolutely can't ignore the layout of the chips themselves. A 2025 breakthrough by Parity QC tackled a massive, massive hurdle. Moving quantum information across a large chip usually requires costly lattice surgery or complicated routing. It's basically a massive traffic jam of swap gates. Parity QC reimagined how we use error correction redundancy. By keeping the code's redundancy in a single basis, they completely bypassed traditional routing bottlenecks. This allowed the system to perform long-range, multi-qubit entangling gates locally. It is just an incredibly elegant solution to the nightmare of moving information across a physical chip. All right, Section 5, Code Breaking and Real-World Impact. Let's see why this matters outside the lab. We've looked at the abstract math and the mind-blowing hardware engineering. But why should you care? One massive reason is cracking encryption. Shor's algorithm is famous for its ultimate application, breaking RSA encryption. But it doesn't do this with some kind of theoretical magic. It relies heavily on modular exponentiation. That means performing massive amounts of plain old quantum arithmetic, multiplication and addition. And that arithmetic, it is built entirely on the backs of the multi-qubit gates we've just been exploring. Let's walk through the steps of this critical arithmetic cycle. First, you compute modular multiplication coherently. Second, you accumulate that product right in the quantum register. And third, you uncompute temporary data to clean up the ancilla, or helper qubits. This step 3 is absolutely vital. Remember our old friend the Toffoli gate from earlier? Reversible gates like Toffoli are used to produce a temporary carry bit, but they must also be used in reverse to uncompute that data. If any junk information is left behind during the uncomputing phase, it destroys the reversibility, collapses the state, and ruins the entire quantum calculation. Which leads us to a final, pretty big thought. If these multi-qubit gates, the physical lasers, the precisely timed microwaves, the reversible Toffoli circuits, are the microscopic engines that will one day break modern encryption, how close are we really to a truly fault-tolerant quantum world? The hardware is scaling rapidly, and gate fidelity is inching closer to perfection every single year. It is an absolutely fascinating space to watch, and I hope this explainer helped you grasp the incredible mechanics driving it all. Thanks so much for hanging out, and keep on learning.